So we are going to start today by stepping away from equilibrium problems, and we're now going to start looking at non-equilibrium problems, right? And we're going to start off by looking at objects on slopes and known directions of acceleration. Okay? So there's going to come a time in a few chapters' time where we will have to work out the direction of acceleration. For the time being, we know the direction of acceleration, and this is very important. So when forces are not in equilibrium, right, that obviously tells us that the net force will not be zero. Okay? And if your net force is not zero, that means that there must be acceleration. And we like to take baby steps. So as I said, we're going to give you the direction of the acceleration, and we will just be needing to calculate it, or we'll have to use the direction of accelerate to possibly calculate the different forces. So if we think back to chapter 2, when we're calculating force, right, we use that equation, force is equal to mass times acceleration. That's just Newton's second law. We will still need to resolve the forces into components in a relevant direction and find the net force. We cannot calculate acceleration in two different directions because acceleration doesn't happen in two different directions. Acceleration only happens in one direction, and it always happens in the direction of the net force. Okay? Now, later on, we're going to have to calculate that direction, but for now, we are going to assume what it is, right, based on the problem, or it's going to be given to us. So if you consider Fred Flintstone running up the hill over there, we can tell that his direction of acceleration is going to be up the slope. Right? Now, obviously, we're making some very big assumptions here, but, you know, based on the diagram we're given, it's quite an obvious assumption that the acceleration will be up the slope. Right? Now, Kiana, why can't the acceleration happen in any other direction? What would happen to Fred Flintstone if the acceleration didn't happen up the hill?
You just at the bottom of the hill.
So what would happen if I change the direction of acceleration not to be parallel to the slope? What would happen with Fred Flintstone?
You'd go backwards.
Well, either he'd go backwards, right? Or what if let's grab that. What if I rotated it like this? If that was his direction of acceleration, it's no longer parallel to the slope, which means that he's built up so much speed and he's got wings on his little thing there, and he's actually going to end up flying off into the middle of nowhere.
Okay.
So that's an assumption that we're making. Hey, it could be possible, right? But we're making the assumption that the object is going to stay parallel to the surface. So that brings up a very important point, and that is the net force in the direction perpendicular to acceleration is zero. So if we have a look at my block object now, it's just a little bit easier to see, right? We can see the direction of acceleration, all right? We're assuming, right, based on the diagram, that the direction of acceleration will be in the direction of the slope. Now, if the acceleration was not in the direction of the slope, let's consider a direction that is perpendicular to the slope. If we had acceleration off in this direction, that would mean that the object is going to move in that direction and would be flying off the slope. I I would be very worried if a box just started floating off up into the middle of nowhere. So when we calculate acceleration, it only happens in one direction, and it only happens in the direction of motion, right? In other words, in the direction where the net force is going. Okay, let's just move on to some examples and see how this works. Okay. Here we have a box of mass 25 kilograms. It's dragged along the floor by a force acting at 30 degrees or 30 newtons at 20 degrees above the horizontal. Right? Find the acceleration and the normal contact force. Right, the first thing we do when we see problems like this is we immediately look and see if we've got the correct lines of action, right? So my unknown force happens to be a vertical force, right? So I don't need to change my perspective and shift my line of action around, okay? So I'm going to keep the diagram as is. Now, just to make it easier, now, like I've always said, you guys will be drawing your components on the diagram itself, but I'm not going to make mine messy, so I'm just going to draw them off to the side here. I can see I have a vertical and two vertical components. I have the contact force of the surface. I also have the weight of the object acting down. And then I have this force over here, which is acting off in that direction. So the first thing we need to do is we need to split this up into two components so we can resolve. Okay, like I said, you'll be drawing this on your actual diagram. I'm just drawing it off to the side just so it's more clear and you can see what we're doing. Okay. Now we're given that this angle is 20 degrees and we know the size of this force as 30 newtons. So if I just label these X and Y, just so that I keep track of them, I can see that X, the size of force X happens to be the side adjacent to 20 degrees, so it's going to be cos, so it will be 30 cos 20 degrees. Y happens to be opposite, so it's going to be sine, so I'm going to get 30 sine 20 degrees. Right, now, because we know that acceleration, we know the direction of acceleration is along the surface, we know that the forces perpendicular to that surface are not going to affect the acceleration. Okay? In other words, any forces that are perpendicular to the acceleration, right? Their net force must be zero. Right? Because if the net force was not zero, that object would also be moving in that direction. That tells me that in my problem at the moment, if the net force is zero, right, because the acceleration is happening in a perpendicular direction, that means my vertical components are in equilibrium. So I'm going to ignore the vertical components and I'm only going to concentrate on the horizontal components because those are the ones causing the acceleration. Okay. So using the simple formula that force is equal to mass times acceleration, right? Let's look at the forces causing the acceleration. So we need to look at the direction the acceleration is happening, right? It's happening in a horizontal direction. And now I need to go and look at the forces acting in this direction. Okay? So the only force acting in the horizontal direction is this horizontal force over here, right? It's one of the components of that 30 newtons, right? Now remember, when we split forces up into their components, we basically ignore the net force of that component. Okay? Because we can't look at all the components. We can't make new forces. So the only force acting in the direction of acceleration is that x component of that force. Right? We have to look at the direction that it's acting in. Right? It's acting in the direction of acceleration, so it's going to be a positive number. And so our force is going to be 30 cos 20 degrees. Right, this is going to be equal to the mass times acceleration. The mass of the object was given as 25 kilograms, and acceleration is the thing we're trying to work out. So we're going to go 30 cos 20 on the calculator, and then divide by 25. And this is going to give you your acceleration as 1.12763 . Right, we can't leave our answer like that. We need to round appropriately, and this will depend either on what the question tells you or whatever stated in the question paper. Okay? The convention is normally 3 significant figures, right? So if I round this to 3 significant figures, it'll be 1.13 meters per second. Don't forget this guy here, please. Just like Charlie, don't forget Charlie. Don't forget that thing either. Right, so we've got our acceleration. The other thing we were asked to find was the normal contact force. So the contact force is the force of the surface pushing up on the object. In our diagram, that's force R. Okay, force R is perpendicular to the line of action or the direction of acceleration, which means that the component forces vertically must be in equilibrium. So if we are resolving vertically now, component force R, or force R, must be equal to oh, I'm actually talking porcupines, aren't I? Let's go and have a look at all the vertical forces before I get ahead of myself. There's a vertical force, there's a vertical force, and there's a vertical force, right? 2 forces are acting in the same direction, and one of the forces is acting in the opposite direction. Because they are perpendicular to the line of acceleration, those 3 forces must be in equilibrium. So force R plus whatever force Y is, the vertical component of the 30 newtons, must be equal to the downward force, right? And that is that 25 kilograms times the gravitational constant, right? So that'll be 250 newtons. Okay, I've got Y, so I'm just going to substitute. R is equal to 250 minus 30 sine 20. 30 sine 20. That's going to give me 239. Well, I'm actually going to write this out for you. 239.7393, etc. Again, the convention is usually to round to 3 significant figures, but please just read the question paper and see what's appropriate. If I round this to 3 significant figures, right, I'm going to get 240 newtons. Okay, everybody cool with that? Nice and easy?
Yep.
Very similar to the physics types questions as well. Okay, let's move on then. Right, here we have a boat, right? Now, in the worked examples, and I've been nice, I've drawn the diagrams, okay? Obviously, you'll notice from the homework questions that you have to draw your own diagrams. So it's very important that you draw them accurately and look at the information given and go from there. So always draw the most obvious forces first, okay? So we have a boat of mass 40 kilograms, right? It has a driving force of 30 newtons in an easterly direction. Okay, so we can draw our first force off to the east of 30 newtons. It's been blown by the wind by a factor T. So in other words, we don't know the wind force, so we're going to call the force factor T for now. And this is to the north. So the wind is blowing to the north, so the force is pointing in the northerly direction. The boat moves on a bearing of 60 degrees. Right, so a bearing, right? Remember, bearings start from north, right? So from the vertical, and then we go clockwise the number of degrees given. So we were told 60 degrees, so we start at north and we go around in a clockwise direction 60 degrees, right? So the opposite way to trigonometry. Okay? Trigonometry goes the other way. Bearings goes clockwise, trigonometry goes anti-clockwise. They want us to find T and the acceleration of the boat. Okay? So this is where we sit in with a little bit of a pickle, because we were usually taught, okay, when we are resolving forces, we like to resolve in the direction, right, or perpendicular to direction of the unknown force. And the unknown force happens to be in the vertical direction, right? The problem is it's not in the direction of motion. The direction of motion is also the direction of acceleration. And so we actually want to resolve in the direction of acceleration, okay? Because we know the forces perpendicular to the line of acceleration are going to be 0. So the easiest way to think about this is to take this picture here and to rotate it in your head. Into that. So now we can see the direction of action. The direction of action is also the direction of my acceleration. And so what I need to do to resolve that is to split those other forces into their different components. Now, once again, you will do this on the diagram itself, but just to make it easier, I'm going to do it off to the side so you can see clearly what I'm doing. Or I could actually do them on the diagram. I'll just do them in a bit of a weird way. Okay? So let's split the components of T and 30 newtons up into both vertical and horizontal. There's the vertical component, and the horizontal component must go in that direction. And we can have a look at that now and see where our angles are. There's our 60 degrees, right? And we can say that's 60 degrees because it's just an alternative angle. Okay, when we draw these force vectors, remember these two lines are parallel to each other. Okay, let's split the 30 newtons one up as well. So we'll have a force going in that direction and a force going in this direction. And again, using the same concept or the same principle, we can work out the angles. Okay. We have a 90-degree triangle here, or a 90-degree angle there, because one bearing is north, one bearing is east. Actually, that's on my original diagram, my apologies. So that's 30 degrees. That makes this 30 degrees. And this angle and this angle here are alternate angles, right? Because those lines are parallel. That tells me this internal angle here is also 30 degrees. Now, again, I'm going to write the components of the two different forces out so you can see them. But again, in the question and when you're answering this, you don't have to write these things out. You can just put them straight into your work. All right, but I just want to show you, there's a vertical component There's a horizontal component. Here's another vertical component, and here's another horizontal component. So just so you can see them and where I'm getting the information from, so it's not coming out of a random place, I'm going to write the two different components out. So let's write the horizontal component of force T. Okay, it is the adjacent side to that 60-degree angle. So it's going to be T cos of 60 degrees. Please stop me if you're confused where I'm getting these values from. Right, the vertical component of force T, that is the opposite side to 60 degrees. So that's going to be sine. So there's the two components of force T, resolved vertically and horizontally. We'll do the same thing now for force, that's 30 newtons force. The horizontal component is also adjacent to that 30 degrees. And so this will be 30 cos 30. And the vertical component is opposite, so it will be 30 sine 30. Right, I've resolved all my forces now, and so we are set up to answer the question. Again, you don't have to write these things out. Your process would be draw the force components, and from there you can move straight into answering the questions. Just for the purposes so that you know exactly where I'm getting these figures from, you can see them now on the screen. Right, let's resolve for force T first, because we have a bit of a problem. We're trying to solve acceleration, right? But in order to do that, we have an unknown force, right? In the line of acceleration, we have a component, right? And one of those components has an unknown. So we'll end up with two unknowns. We'll have an unknown in the acceleration, and we'll have an unknown in force T, right? However, we now know that forces perpendicular to the direction of motion or the direction of acceleration are going to be zero. The net force of that must be zero. So they must be in equilibrium. So if we solve vertically first, we can actually solve for force T. So let's solve vertically first. Let's identify the forces that occur vertically. And they just happen to be the two component forces that I've just separated out. So they're acting in opposite directions, and because they're perpendicular to the acceleration, their net force must be zero, and so they must be equal to each other. They must have the same magnitude. So my vertical forces are T sine 60 and 30 sine 30. And from here, we can just now, From here, we can just punch this into the calculator, right? So we would go 30 sine 30 divided by sine 60. And we're going to get 17.3205, etc. Okay. This is 4, so we're most likely going to round to 3 significant figures. So T is equal to, well, actually it's approximately equal to 17.3 newtons. Right, so from here now we've got the magnitude of size T, and so we can calculate the acceleration, right? So when calculating acceleration, we need the force and the mass, right? We need the force in the direction of acceleration. So we need to go and look at the components that make up the force of, well, in the direction of the acceleration. The acceleration is happening horizontally, and so we need to look for all the horizontal components acting in that direction, right? And they happen to be the two x components here, right? They are happening in the direction of acceleration, both of them, right? So we must add them together, right? They will both be positive. So t cos 60 plus 30 cos 30 must be equal to the mass of 40 times the acceleration. Right, just to save some time, I'm just going to give the answer as 0.866. That's rounded to 3 significant figures, meters per second squared. Right, remembering that we know the value of t, and because we are using trigonometry, don't use your rounded figure from the previous step, right? If you have to go back and recalculate that force, recalculate it so you have the exact value on your calculator, and then use that immediately to work out the next line, t cos 60 degrees, right? Remember how trig ratios are very sensitive to decimal places. Right, one more to go. Right, in this question again, we have a slope, right? So my assumed direction of acceleration is going to be perpendicular or parallel to the slope, okay? We're making an assumption that the object is not going to go flying off the slope into the middle of nowhere, right? We're assuming that it'll follow the path of the slope. We are also assuming that the weight is not more than the contact force, so this object's not going to be pushing into the ground, right? So the first thing you would have had to do is draw this picture, right? So your force diagram, labeling all the forces that are occurring. And if this was a problem where we had the forces in equilibrium, we could have chosen a direction or line of action, right? Except now the line of action is going to be the direction of acceleration, and that is going to be up the slope. So we have a resistance force up the slope, right, of 10 newtons. And we're told that the table takes 5 seconds to slide 10 meters down the slope from rest. And we want to find the mass of the table. So we need to rack our brains back all the way to chapter 1 and then think, okay, we've been given some information here. We know the initial velocity is 0 because it's started from rest. It slid 10 meters down the slope, all right? So my displacement here, well, the displacement will depend on the direction that you choose for acceleration. So you can choose acceleration being down the slope or up the slope, right? Because the object's moving down the slope, we can just maybe say that this direction here that's the direction of acceleration. Okay? It's the direction of motion. Anything in that direction is positive. Anything in the opposite direction is negative. That means that the table has moved a total of 10 meters. Its displacement is 10 meters. And we were told that this takes 5 seconds. Right, so we have 3 pieces of information, and if we know for constant acceleration, right, again, we're making the assumption that this thing is accelerating at a constant rate. Right, so that's the formula that we'll be using, right, because it's the one that allows us to solve in one step. And here we just plug the information that we have in and solve for the acceleration. So we have the displacement of 10 meters, no initial velocity, And we have time of 5 seconds squared. But that will give me an acceleration of 0.8 meters per second squared. Okay, now that I have the acceleration, I can start to work out the forces. Okay? So we want to work out the mass of the object, right? And in order to calculate the mass of the object, we need to know what forces are acting on that object in the direction of the acceleration. Okay, so if we have a look at the acceleration of this table, we can see that the contact force, right, is acting perpendicular to the acceleration. In other words, the contact force is not a factor in determining the net force in the direction of acceleration. Right? What will play a factor is going to be this resistance force over here, because it's parallel to the direction of acceleration. And you can see we have this weight force down here. It's going to get split up into a horizontal and vertical component, right? We are not interested in the force acting perpendicular. We're only interested in the force acting parallel. Right, so we don't know the weight of this object, so we're just going to call it mass times g, so it's going to be 10m. And just quickly, I'll draw it in, but we are just interested in that component of my weight. Okay, we're not interested in the component perpendicular. So I'm going to just finish off my triangle here. I just need to get some angles. I can see I've got a bunch of triangles here. This is 20 degrees, so this must be 70 degrees. And because it's a 90-degree triangle, this must be 20 degrees. So this force over here, that is the opposite force from 20 degrees. And so it will be 10m, right? Because the gravitational constant is 10. And it will be sine of 20 degrees. Okay? That's happening in the direction of acceleration, right? The other force, the minus 10 newtons, that's happening in the opposite direction. And this must be equal to the mass of the object, right, which is unknown, we're trying to solve, and the acceleration of 0.8. The rest is just calculator work and solve for m.